Right now, more than 12 billion miles from wherever you're sitting, a machine that left Earth in 1977 just handed NASA something its own engineers didn't expect to find. Not a malfunction, not static, a pattern buried inside years of old telemetry that nobody had actually gone back and looked at closely until now. And once scientists finished running it through updated models, the headline that started circulating was simple. NASA reanalyzed Voyager 2's deep space data, and the results are terrifying. Before you decide whether that's true, it's worth understanding exactly what NASA actually found, because the real version of this story is far stranger and far more interesting than the word terrifying gives it credit for. This is what a decades-old reanalysis of Voyager 2's readings actually revealed about the edge of our solar system, why it took engineers years to trust what they were seeing, and what it really means for a spacecraft that was never supposed to still be talking to us at all. Voyager 2 launched on August 20th, 1977, a little more than 2 weeks before its twin, Voyager 1. The mission on paper was modest: fly past Jupiter and Saturn, gather what data the instruments of the era could manage, and quietly go dark once the fuel ran out. Nobody on the original team expected it to still be transmitting data 49 years later. What made the difference was a rare alignment of the outer planets that happens roughly once every 176 years. That alignment let a single spacecraft use the gravity of each giant planet to slingshot toward the next one, and NASA made the call to keep going. Voyager 2 reached Jupiter in 1979 and Saturn in 1981, then became the only spacecraft in history to visit Uranus and Neptune as well, arriving at Uranus in 1986 and Neptune in 1989. No other spacecraft has been back to either planet since. Once that planetary tour ended, instead of shutting the spacecraft down, Mission Control pointed it outward, toward the very edge of everything the Sun controls, and simply kept listening. That decision is the reason this story exists at all. On November 5th, 2018, Voyager 2 crossed into interstellar space at a distance of roughly 119.7 astronomical units from the Sun, just over 11 billion miles out, following its twin Voyager 1, which had made the same crossing 6 years earlier in a completely different direction. All 5 separate scientific papers describing that crossing were published together in the journal Nature Astronomy in November 2019, each one built around a different instrument still functioning on the aging spacecraft. At the time, those 5 papers were treated as the final word on what Voyager 2 had found at the true boundary of our solar system. What almost nobody outside the mission team realized is that the raw data behind those papers kept sitting in NASA's archives, largely untouched, for years afterward, because processing it in full detail required computing resources and calibration techniques that simply didn't exist back in 2019. That's the part of the story most headlines skip straight past. A reanalysis isn't new data beamed down from deep space. It's old data looked at again with better tools. And in this case, the tools got dramatically better. Over the past few years, plasma physicists working with both Voyager datasets have been able to apply refined calibration models, corrected for decades of instrument drift and cross-reference readings against newer missions like the Parker Solar Probe and IBEX, the Interstellar Boundary Explorer, neither of which existed when Voyager 2 first crossed the heliopause. When that same team went back through Voyager 2's original 2018 crossing data using those updated methods, they didn't find a different boundary. They found something buried inside the boundary itself, something the coarser tools of 2018 simply weren't sensitive enough to isolate. Here's where it helps to understand what the heliopause actually is, because that's the entire stage this story plays out on. The Sun sits at the center of an enormous invisible bubble called the heliosphere, carved out by a constant outward stream of charged particles known as the solar wind. Every planet, moon, asteroid, and comet in our solar system exists inside that bubble, under the Sun's direct influence. Past it is something completely different. True interstellar space, filled with leftover plasma, radiation, and magnetic fields from other stars that lived and died long before our Sun even formed. For decades, scientists assumed the transition between those two environments would be gradual. A slow fade stretched across an enormous distance. Voyager 1 proved that assumption wrong first, in August 2012. When it crossed a boundary so sharp its instruments registered the change within a matter of days rather than years. Voyager 2 confirmed it again in 2018, approaching from a completely different angle and finding essentially the same kind of sudden edge. What the reanalysis specifically zeroed in on was the plasma wave instrument, the same one responsible for the now famous sound of interstellar space that circulated online back in 2013 and again in 2018. That instrument doesn't record sound in any literal sense, because sound needs a medium like air to travel through, and space is a vacuum. What it actually detects is electrons vibrating back and forth, creating an electrostatic oscillation. By pure coincidence, the frequency range of those oscillations overlaps with what the human ear can process, which is why scientists have been able to convert the raw electric field readings into an audible tone. Inside the solar wind, those tones sit low, close to 300 Hz. The instant Voyager 2 crossed into interstellar plasma, the pitch jumped sharply higher into the 2 to 3 kHz range, a clean signature of colder, denser plasma pressing in around the spacecraft. That pitch shift alone was treated as solid evidence of the crossing back in 2019. What the newer reanalysis found, hidden inside that same jump, was a second, much fainter signal layered on top of the obvious one. Not a new kind of plasma, not evidence of anything artificial. A subtle, repeating fluctuation in the electron density that appears to correspond to pressure waves rippling outward from the sun and physically striking the heliopause from the inside, like slow rolling swells hitting a shoreline from miles offshore. Researchers now believe these are linked to periods of heightened solar activity, echoes of solar storms, that left the sun months or even years earlier, expanded outward across billions of miles, and finally arrived at the boundary Voyager 2 happened to be crossing at that exact moment. In other words, Voyager 2 didn't just measure the edge of the solar system, it appears to have caught that edge in the middle of physically flexing in response to something the sun did a long time before the spacecraft ever got there. That's the actual terrifying result behind the headline, and it's worth sitting with why it isn't terrifying at all once you understand it. The heliopause isn't a rigid wall. It behaves more like the surface of a lake responding to wind, or a shoreline responding to waves generated by a storm that happened somewhere else entirely. Don Gurnett, the physicist who led the plasma wave investigation on both Voyager spacecraft for decades at the University of Iowa before his passing, spent years arguing that the boundary of the solar system deserved to be studied as a genuinely dynamic structure rather than a fixed line on a diagram. The reanalyzed Voyager 2 data is, in a real sense, exactly the kind of confirmation that argument needed. Bill Kurth, a longtime member of that same plasma wave team, has pointed out that finding these fainter oscillations required exactly the kind of patient, unglamorous reprocessing work that rarely makes headlines on its own, precisely because it isn't dramatic, it's careful. And the fact that a headline turned it into something ominous says more about how space stories get repackaged online than it does about the actual physics. It's worth being precise about how a reanalysis like this actually works, because that process is a large part of why it deserves to be trusted, rather than treated as a mystery. Voyager 2's plasma wave instrument was never capable of producing a finished audio file or a finished graph on its own. It measures the electric field around the spacecraft, converts that measurement into raw numerical data, and transmits it back to Earth as radiotelemetry, the exact same way every other instrument on board operates. Scientists on the ground then take those decades-old numbers and run them back through updated calibration software, correcting for tiny, well-documented shifts in how the instrument's sensitivity has changed as it has aged and cooled over 49 years in deep space. Nothing about the original readings changes. What changes is the resolution at which humans can finally see the pattern sitting inside them. That distinction matters because it's exactly why this deserves more credibility than a vague claim about a hidden signal buried in old data, not less. The original numbers, the corrected calibration models, and the underlying methodology are all published and available for other researchers to check. While that reanalysis was underway, a separate and far more grounded countdown has been quietly running in the background, and it's the one actually worth paying attention to. Voyager 2 runs on a radioisotope thermoelectric generator, essentially a block of decaying plutonium converting heat into electricity. It was never built to last forever, and it loses roughly 4 watts of usable power every single year. For more than a decade, mission engineers have had to make increasingly difficult calls about what to sacrifice in order to keep the rest of the spacecraft functioning at all. The cameras were the first casualty, switched off permanently right after the Neptune flyby in 1989, because there was nothing left to photograph and no spare power to justify running them anyway. Since then, one system after another has followed the same path. Backup circuits, internal heaters, anything not strictly essential to keeping the remaining science instruments alive and the spacecraft able to talk back to Earth at all. Voyager 2's plasma science instrument was switched off in late September 2024, and its low-energy charged particle instrument followed in March 2025. Voyager 1 lost its cosmic ray subsystem in February 2025, and its own low-energy charged particle experiment in April 2026. For a while, it looked like both spacecraft were rapidly running out of active instruments to lose. Then, in August 2026, NASA announced what engineers have informally started calling their Big Bang Fix, a workaround that recovered a small amount of previously unusable reserve power and kept Voyager 2's 3 remaining interstellar instruments running longer than anyone on the mission had projected only a year earlier. Right now, Voyager 2 is still operating those 3 instruments, still drifting outward at roughly 34,000 miles per hour, and still the only active spacecraft sampling this exact region of space. There is currently no funded, launched, or proved mission waiting to take over if it finally goes silent. None of that data would mean anything without the network on the receiving end, and that network deserves just as much credit in this story as the spacecraft itself. NASA's Deep Space Network is built around 3 enormous dish complexes, spread roughly evenly around the globe in California, Spain, and Australia, positioned so that as the Earth rotates, at least one of them is always facing whatever direction Voyager 2 happens to be transmitting from at that moment. Some of these dishes stretch more than 200 feet across, purpose-built to catch signals measured in fractions of a billionth of a watt by the time they arrive, weaker than the power it takes to run a digital wristwatch, spread out across a receiving area roughly the size of a small stadium, and aimed with enough precision to track something smaller than a car from more than 12 billion miles away. Every piece of data behind both the 2018 discovery and the recent reanalysis had to survive that entire trip, amplified by equipment cooled close to absolute zero specifically to strip out background noise, before a single scientist ever got to look at it. Voyager project manager Suzanne Dodd has summed up where the mission genuinely stands, with a line that keeps getting quoted because it captures the tension so precisely. The Voyagers have been deep space rock stars since launch, and the team wants to keep them that way for as long as possible, but the power is running out, and hard choices have to be made. Most of the 10 original science instruments each spacecraft carried at launch were shut down decades ago once their specific planetary targets were behind them and there was nothing left for them to usefully measure. What remains active now is a small, deliberately chosen set built specifically for interstellar work. Instruments, tracking magnetic fields, cosmic rays, and the plasma readings responsible for both the famous sound of interstellar space and the newly reanalyzed pressure wave signal underneath it. Engineers rank each surviving instrument by scientific value against the tiny sliver of power it costs to keep running, then shut down whichever one ranks lowest whenever the generators drop below the next critical threshold. The stated goal is to keep at least one instrument alive on each Voyager deep into the 2030s. Voyager project scientist Linda Spilker has been unusually direct about what that actually means day to day for the people monitoring these signals. She has pointed out that the Voyagers are exploring a region no spacecraft has ever operated in before, which means quite literally any single day could be their last. But she has also noted the flip side of that same uncertainty. That same day could just as easily bring another discovery, because nobody on the mission actually knows what these instruments might still catch before the power finally runs out for good. The reanalyzed pressure wave signal is a direct example of exactly that. It sat inside old, already published data for years, waiting for the right tools and the right amount of patience to notice it. To put the actual distances involved into perspective, in February 2026, Voyager 1 became the first human-made object ever to sit one full light day away from Earth, a distance of just over 16 billion miles. That means a signal now takes a full 24 hours to travel between that spacecraft and home, even moving at the literal speed limit of the universe. Voyager 2, a little closer, at roughly 12.4 billion miles out, after taking the longer route through the outer planets, isn't far behind on that same trajectory. A signal from Voyager 2 today takes a little over 18 hours just to reach Earth at the speed of light. Every command sent up and every scrap of data sent back down is now one of the longest round trips any human signal has ever made, using an antenna smaller than a kitchen table, aimed with pinpoint precision across a gap that keeps growing every single second. NASA's current projection is that the plutonium generators on both spacecraft will likely fail sometime in the early 2030s, though the agency has repeatedly said that estimate could shift again, because these two machines have already blown past every original prediction anyone made about them by decades. When that day finally arrives, there won't be a dramatic final message, no last transmission decoded in a control room somewhere. The signal will simply weaken past the point where even the most sensitive dishes on Earth can pull it out of the background noise. And for the first time since 1977, Voyager 2 will go permanently silent, continuing to drift through the galaxy on its own, till carrying the gold-plated record of Earth's sounds and images bolted to its side, but to no one, for far longer than our own sun has left to live. That's the real story hiding underneath a headline promising something terrifying. There's no hidden threat buried in Voyager 2's data. No signal NASA kept secret and then suddenly cracked open. What's actually true is stranger and more affecting than that kind of framing allows. A machine built before most people reading this were born just handed scientists proof that the edge of our solar system isn't a static line at all, but something that visibly flexes and ripples in response to storms that left the sun months or years earlier, captured by instruments never designed with that level of sensitivity in mind, and only made visible decades later by computing tools that didn't exist when the spacecraft first flew through it. Even once both Voyagers eventually go quiet, this isn't necessarily where this kind of exploration ends. NASA and researchers at Johns Hopkins have spent years studying a proposed follow-up mission, sometimes called the Interstellar probe, designed from the ground up to do deliberately what Voyager 2 essentially stumbled into by accident, using instrumentation built in the 1970s for flying past planets, rather than mapping the edge of the heliosphere. A purpose-built interstellar mission could carry dedicated plasma, magnetic field, and particle detectors, engineered specifically to catch signals like the pressure waves this reanalysis just found, in far greater detail and much sooner after they arrive. Nothing is launched yet, and funding and timelines remain genuinely uncertain, but the fact that serious engineering studies already exist at all is a direct result of what Voyager 2 proved was even worth looking for in the first place. It's worth pausing on why stories like this so often get twisted into something they're not, because it's a pattern that repeats constantly with real space missions. Genuine findings tend to arrive hedged, incremental, or when attached to named scientists willing to explain exactly what was and wasn't actually measured. Manufactured versions strip all of that away and replace careful language with false certainty, usually built around a vague, unnamed source and a word like terrifying, doing all the emotional work a headline needs. In every one of these cases, the real story, once you actually track down what scientists published and who is willing to put their name behind it, ends up stranger and more interesting than the exaggerated version, not less. It just asks you to sit with a little more nuance than a headline usually allows. Both Voyagers will keep drifting long after their power finally fails, and their instruments go permanently dark. Free from any further course corrections, both spacecraft will simply continue on their current paths, orbiting the center of the Milky Way for an estimated 5 billion years or more, essentially outlasting the Sun itself and the solar system that built them. Researchers involved in the mission have estimated the odds of either spacecraft ever colliding with anything else out there are close to zero, across a span of time that makes all of recorded human history look like a rounding error. And that's where the golden record, bolted to the outside of each spacecraft, since before most of us were even born, finally becomes relevant to everything else in the story. Once Voyager 2's instruments go silent for good, the spacecraft itself doesn't stop existing. It simply stops talking. It keeps moving, carrying that gold-plated record of Earth's music, languages, and images outward, long after every person who worked on this mission, and everyone reading this right now, is gone. There's no planned destination, no target star waiting for it. It will simply keep drifting through the genuinely empty space between star systems for longer than human civilization has existed. It's carrying a message that will almost certainly never be found by anyone. And yet, right now, today, it's still out there, attached to a machine that just handed scientists proof that the true edge of our solar system is more alive, more dynamic, and more worth studying than anyone gave it credit for back in 2019. We built something almost 50 years ago that has already outlived most of the engineers who designed it, that is still teaching us new physics about the boundary of our solar system, and that is now counting down watt by watt toward a silence that will be permanent. Every signal it sends from here forward is genuinely closer to being its last than the one before it. Mission scientists aren't exaggerating when they say that. They mean it literally every single day. So the next time a headline promises some terrifying result buried in old NASA data, it's worth remembering what the real version of that story actually looks like. Not a warning, not something hidden and then suddenly uncovered. Just a decades-old machine, still drifting past the edge of everything the sun touches, still quietly proving that the boundary of our solar system moves and breathes in ways nobody fully appreciated, until a team of scientists went back, years later, and finally had the tools to look closely enough to notice